Ah, Sarah, mon recording va loop pas.
No
Sorry.
worries, it's okay. Okay,
So
that's fine.
you're going to miss the start. Okay, so in Indonesia, you're going to have the material piling up down the volcanoes and down the mountain into the trenches and in those areas. So all of that are sediment with a lot of carbonate inside, a lot of water inside. And when the material goes down in the subducting plate all together, it's like squeezed into sandwich and all of that goes down. When it goes down in this area and is being melted up and heated up again by compression and also by the heat underneath, when it goes up, it's a mix of sediment material and plate material. And that's why you have actually Mount Merapi explosive activity, Raung, and all of those volcanoes that create the explosive activity. If you are around here, you don't have sediment. There is no land. There is no island. So at the bottom here, we only have the lithosphere, that very dark lava material. So that when the material is going up the column, what we have from here is very different from what we have here. In English, this is called magma differentiation. So that's one of the main processes that explain, at least for Java Island, a lot of the relief and the mountain. Of course, you have also tectonic activity bringing up the mountain. So mountain and of course faulted relief, for instance. So when you think about the area of Baron in south of Jakarta and south of Surakarta, this area is made of material from the sea that has been pushed up. So you have your volcanoes and you have the material coming from the sea and material from the sea. Okay. So that's the main driver at the back. So how do we get those relief more exactly? So they are the result of what we call a stress and strain relation. So when you have extension stress or tension stress, so things are being stretched out, you're going to have a thickening of your crusts or of your material, not thickening, thinning, sorry. And then you get a thing like this. You get these kind of things, but you also get normal faults due to the extension. When you have a graben, for instance, it's typical. Another element that you can have is the compression. That's the opposite. So meaning things are being pushed against one another, and you get folding and more preferentially reverse fault. This being said, it's not the only type. You can have a normal fault when you have compression. It's a mix of different elements together, of course. And then you have shear. So the shear means that things are actually being deformed. And it's going to create this kind of horizontal bending in your landscape. So when you have time after this lecture and you review that, what I invite you to go and do is to open your favorite Google Earth and Google Map or whatever you want, and you look at the Progo River and the Sungai Progo in the northern part near Borobudur or in near a bit to the south. It's showing a lot of this. You can see that the river goes straight and then it goes into a U shape. That U shape is typical of this kind of shear, and it's typical of a fault line going through. So one game that you can do as a geographer is to look at your rivers and look at the shape of your rivers. And shape of rivers usually give you a very good indication of what kind of processes are happening. When you have, let's say, a normal fault like this, the river is going to incise and eat back by erosion the material on top. But at the same time, this erosion is going to give you an indication of where the normal fault started and where it's located in the landscape. So all of those elements are very important. And if you're interested in that, actually, Aditya Saputra is a specialist of looking in faults in the landscape. He worked for his PhD on it. He has done very interesting work on those elements. And as a result, we get this map of the world where we have extension location, where the crust is being created, and various compression zone, where Indonesia, unfortunately, is like mixed on both sides, but that's where actually your country is located. And you can see from Papua New Guinea and Papua that all of this area, and Japan, where I am, is all very complex. It's all meshed and mushed together. So today's topic is about the opposites. Here we are building relief. We are making the mountain higher and higher, but mountain doesn't go and climb until the crazy height. They get eroded at the same time. So we have on one side the endogenic processes that are going to push things up. And we have on the other side, the surface processes that do the opposite. They bring things down. So those erosion processes can also happen when the earth is flat. You don't need always to have a slope. So here I was talking about the slope. You have your slope here, you have your endogenous processes here. But at the same time, you can also have erosion when it's perfectly flat. So how does it happen? Well, you can have this kind of erosion features that are chemical erosion that you can see in the karst area. I believe that you have karst specialists in your university, so they might talk about it as well. And it creates this kind of dolin and small lake features where actually all of those areas are places where you have dissolution of the material creating those features. And when you think about it, when you have all those pipes in the karst, I was telling you about Baron, the area of Baron in south of Yogyakarta. Baron is typical of this kind of location, where you're going to have a lot of different landforms that are not related only to the tectonic. They are related to the dissolution of the material. So this is chemical weathering. So it's quite different, and it can happen even when it's flat. And when you have the limestone, which is being dissoluted and moved in a pipe, you can see that it also deposes on the side of the pipe, but at the same time, it's also eroding, creating holes like those ones here. So that's the type of things that you're going to have. When you have a valley, usually you're going to have also elements that stop the water actually from disappearing inside. So here I'm going to be giving you also the different vocabulary elements for karst geomorphology in English, with the sinkholes, which are those small holes that you can see, exactly like what you have here. Like this small lake here is the result of a sinkhole. And you also have those small valleys with no water, which are the karst valley here. Okay, so have a look at it and have a look at how do you call it and name it in Indonesian. Do you have actually in Bahasa a different conception than what you have in English? Now, if we can have erosion on flat areas, the element that works miracle and that explains most of it, the erosion, is the slope. So when you have a slope, this is when you actually get most of your erosion. And let me move one thing. Okay. This is when you have your erosion. So when you look at this schema here, you can see that we have the drier elements, or less water, against more water on that side. So that's a way to divide the different landslides. And we have the fast, quick landslides against the slow landslides here. Okay. So that's based on the water content horizontally, and vertically we have the rate of mass movement. So rate of mass movement doesn't mean much actually, it's more like the speed at which they occur. So if we start from this dry and fast, we have the rockfall. So rockfall are elements from the top that will collapse by gravity. And because there is very little element that stops, they just fall through the air. That's why actually those are very, very, very quick. There is little time to just actually hide away from them. They can be triggered naturally, so by logical normal erosion, but also by earthquakes. Earthquakes are very good at triggering those elements. And one of the way they will occur is like if you are on a cliff just by the sea. Imagine that's a cliff, F. You have the water of the sea, which is just right here. So that's the sea. Okay. And the sea is going to erode all of this. And when the sea erodes the bottom, the top part is going to be weaker, and then it's going to collapse. This is called regressive erosion. It's typical of this kind of mass movement. Now, we are on very dry. If we add a bit more water, we're going to have the debris avalanches. Okay, debris avalanche is a difficult term because it is also used for very huge mountain collapse, not only the type of landslide. So let's forget for 1 second the huge mountain collapse and look at the debris avalanche as a type of debris flow, or not debris flow, sorry, a type of landslide, mass movement. And what we're going to have is a lot of large stone mixed with water and sediment all together. There is no consistency. You can see you have a lot of small elements on top of each other. And usually this can be triggered either by gravity only, like an earthquake with acceleration, but very often it's going to be related to rainfalls. And then when you move from that into the wetter area, so you have more water, we have here the mud flow or the debris flow as well. So mud flow is not a term I really like much, but it's all the debris flow together. And they will be confined into a valley and then spread out. On a volcano, this type of mass movement will be called a lahar, which is a term that comes from your country, so I'm sure you're very acquainted with it. Okay, and when you have those mud flow, usually you're going to have this kind of results downstream. If you have seen the lahar or the banjir that from Merapi volcano, you are going to see these kind of results downstream. Okay, so this is very fast. Maybe this one is the fastest because it has almost nothing that stops it. And then in between, you have this one and this one. And debris flow will be usually a bit faster than some typical water flow. Let's go up a bit and look at the slower elements. So the first element, which is quite slow, is called the soil creep. So when you have soil creep, you have more water than this one. So if you think about dry, this is super dry here. And the other here are actually a bit wetter, a bit like this. And in that case here, because you have a soil, you do have water. And what is happening is that you have the rock, the regolith here underneath. And on top of it, you have a soil. And that soil is not a good friend with the regolith underneath. So they don't like each other so much. So they don't bound, they don't stick. And you have a creep. The creep is not regular. It's like when you have your both hands together. When the creep occurs, you're going to have actually what we call buckling. And you're going to create small waves like this. I'm sure your teacher will remember, Aditya will remember, in New Zealand, you see a lot of those features. You have very steep slope and the soil that cripple on top while it's moving. This is very slow and it doesn't require a lot of rainfall. It's just normal condition. It's just going very, very, very slowly on the slope. And then you have the landslides that need a bit more water. So we have all of this here in the center. So those ones need heavy rainfall. They need often rainfall, an earthquake to be triggered. But we have made a differentiation between the slump or rotational landslide, the earth flow, and the translational slide here. So what is the difference between these three? Well, as you can see, it's the structure, how it's made. So for the slump or the rotational landslide, is going to move on that loop here. For the earth flow, it's going to be quite linear. And for the translational landslide, you're going to have something which is a bit more linear. And you have blocks that all go down parallel one to another. Okay? And then in the end, we have the solifluction. So solifluction is very close to the soil creep, but it requires a lot of water. You find those more, especially in very cold region of the world. So because you are from Indonesia, I thought that it was important to present to you something that you might be more acquainted with, debris flows and debris flow on volcano. So in other words, lahar. But before we get there, I am going to give you a break on this lecture, and we are going to, hold on a second, go to this element here. So what I want you to do now is to take the Geomorphologie Leerlingbukket handout that I gave you. And I'm going to give you a few minutes to read those, okay? You read those elements. And we are going to ask the first question, why in the above example, in that equation, we can ignore the time derivative? And I might ask someone in the team, okay? So I have a list of names here. Shafa, Sophie Suja, Adefaja Kurnia, and many, many, many others. And what I'm going to do is to ask some of you questions and ask you to answer this question. So Valerina, I can see you in here. What I can do is to ask you to unmute and ask you a question. Okay? So I give you 5 minutes to read this and think about the question here. Boleh?
Oke, Chris.
Ya.
Baik, teman-teman, Profesor Christopher Gomez meminta kita untuk membaca material tersebut 5 menit. Kemudian kita mau diskusi tentang pertanyaan yang ada di question mark di box itu di bagian bawah untuk menjawabnya. Nanti akan ditunjuk secara random kira-kira jawabannya apa. Tapi jangan khawatir, saya kira we can deliver it in English or in Indonesia ya. Language
terserah.
Ya, terserah. Oke, silakan dibaca terlebih dahulu.
Thank you, Aditya.
You're welcome.
So when they are doing it, I wanted to ask you, is it too difficult for them to look at those equations? Are they used to it, or do you do?
The equation is not too difficult. I think it's not too complicated. So I think it's fine.
Yeah. Okay.
But I'm not sure about the third column. The equation in the third column maybe is a bit complicated.
Okay. So it's 11:30. I'm going to give them 5 minutes. Maybe because it's the first time it's in English, it's maybe easier if I give the answer. What do you think? Oke, ke kiri ada persamaan diferensial ya. Kenapa kita bisa mengabaikan turunan waktu di persamaan diferensial ini? Why can we leave out the time derivative in this equation? So you can see you have the change here of Qx, which is the mass discharge of the regolith in space, over X. So for each box X here, you have actually a various discharge. And why I think that the time is not necessary here. Okay, so I'm going to give you the answer. I think I should maybe not ask you for the first time. It's a difficult question. So in this, so in this equation here, the erosion rate is only dependent to the rock density and the bulk density of the regolith. So it's not dependent over time. So with time, it's not going to change at all. So the time derivative here will not give you extra information so that you can get it out of the equation. So that's actually your equation here of the weathering rate is going to be only a function of the position, and that position will give you actually an information on this, the slope of the location and how much sediment you have. That's all. So it's a very easy equation, and that equation will give you or relate to an equation which is in the family of the heat diffusion equation. And if you want to have a look at the heat diffusion equation, we can look at this equation here. This is the diffusive process equation. So that's the typical equation that you're going to use for your diffusive process. Here, M and N can be constant, and they can be kept as 1 and 0. M equals 0 and N equal 1 to keep the equation simple. Otherwise, you're going to have actually a different family of differential equation, which is much harder to solve. Okay, so when you have a diffusive cave and M equal 1 and N equal 1, in other words, the regolith discharge depends solely and linearly on the local slope, and that's why here we didn't need the time constraint. Yes, Aditya.
Yes, Chris. I just want to clarify for the first question. Why in the above example we can ignore the time because what you say is about because the soil creep is typical of long-term mass movement.
Yeah.
So the time value is not very important in this equation.
Yes, that's correct.
Right?
Yes, correct. So the answer is actually here on the right. That's what I'm showing here. The regolith discharge depends solely and linearly on the local slope dx, dz dx. So that's the local slope, and that's the only parameter that change over space. So as you are saying, over long term, there is no differentiation due to time. So later, if you want...
So I translate it to Indonesia or?
Oh yeah, you can if you want to.
Yeah, because it's important information, I think. So teman-teman, tadi kenapa waktu tidak penting ya katakanlah dalam rumusan dalam menghitung soil creep, karena memang soil creep adalah typical mass movement atau gerak massa batuan yang time onset-nya cukup lama. Jadi ada tidaknya value waktu di situ tidak begitu berpengaruh terhadap besar kecilnya soil creep yang terjadi. Di sebelah kanan itu sudah terlihat soil creep sangat tergantung pada regolith discharge dan slope ya, slope. Jadi seperti itu penjelasan dari tadi sedikit kurang lebihnya ya penjelasan dari Profesor Gomez. Okay, thank you, Chris. You can go on again.
Okay, so that brings me to my second question here. From the last equation above, so from that equation here, where you have the change of the regolith over time, and I'm asking you from the last equation above, explain how the slope shape will change with a fixed downstream boundary condition, kept constant and varying over time. So let me try to see if I can use a whiteboard. New share, whiteboard. Okay, so in that equation above, where we have over time the regolith, imagine that's your slope. So we are in X here and in Z here. And we have a slope that looks like this. The equation says that the rate of change is a function of dz dx. So it's a function of the slope. So for this location here, let's say we have one slope angle here. And we have another slope angle here. And a third one right down at the bottom. The rate of change will be a function of that. So all of this will have the same rate of change over time. And same, that's going to be another one here, 2, 1. And the end. So my question is like, if this here, which is one of the boundary condition, if this is kept at 0, meaning that the material that travels down get eroded, so it's going out, no material stays on the slope. The question I'm asking you is what happens to the slope? Well, because this is always kept at 0, you're going to have the slope, which is not going to change here. So it's going to go back and you're going to have erosion that looks like this. As you can see on this drawing, the erosion here I have drawn on purpose is a lot compared to this, because the erosion is a function, of the slope. Then because we have a big slope here, we have a lot of erosion. We have a small slope here, we have less erosion. A big slope here, a lot of erosion. And that stops. The other possibility that you have, so I'm going to write it down here, because the erosion is a function of the slope, slope angle big equal erosion rate, like in this area. And when it goes down, you get something which is much smaller here. Okay. Another possibility when you are using your differential equation is to modify here your boundary condition. So in the previous example, my boundary condition was always 0 at the end. But if you allow the boundary condition to change, let's say when you are solving your differential equation, you're going to have a node x plus 1, and then your boundary condition here. When you transfer the sediment with the diffusion equation, so the diffusion equation was dqx of dx, you can decide not to keep your boundary condition at 0, but have the sediment pile up. And as a result, the slope here will be reduced a lot. So you're going to have less erosion. And this one is going to be about the same. So you're going to have something like this, then like this, and like this. Okay, so that's going to be your time T1, T2, T3. And you can see how important that equation is. So if I go back to, hold on a second, can I see what I'm doing? Okay, so I'm going to share again my screen, new share, desktop share. Okay, so if I go back to that equation here and this equation, depending on how you solve it, so at the bottom here, what boundary value you're going to use, you can make a lot of different model of erosion based on that. So think about Merapi volcano, for instance. So we're going to look at and think about Merapi volcano. We're going to do new share, a whiteboard share. Okay, so I'm going to erase all of that. So you have for Merapi volcano, your volcano, and you have an eruption and reduce gamble that goes down. And if you keep your lower limit at 0 here, what does it mean? It means that you can have, for instance, Progo or Elo rivers eroding the material so that the Progo river stays at the same level. So when you look at your erosion over time, you're going to have erosion that looks like it's not changing here, but it's going up and eroding like this. Now, if you are in a location where there is no Progo river and you have, let's say you are in Boyolali area where there is no large river, in that case, the sediment that have accumulated here, they are going to, here the slope is important. So you have your slope here, which is very big, but you can allow the sediment to accumulate, and go up. So one equation, only one equation for two different types of processes, erosion and deposition without erosion downstream, or erosion with no deposition with everything eroded downstream. So for geomorphologists, it's very useful because you can test scenarios what happens when you have volcanic material that pile up and it's eroded by a river downstream. But what happens when the material piles up and there is no river eroding, or when you have a change in tectonic, etc. So for instance, when you do your model, you can use MATLAB or R or Python, and this is your timeline. And this is BC, your boundary condition. You can start with a boundary condition which is free. So it's equal to the change of material coming in. So there is no erosion. And then you can decide at T, let's say 10 years or 20 years, that you have a flood or you have some event that erode the material, then you modify your boundary condition. And you can look at what is the effect of that on your landscape. Okay. The second part of the handout I gave you is after that on the rain splash and rain splash energy. This is simple. So I let you have a look at it and look at how rain splash plays a role on the slope. So this is something you can do on your own. And for the last question, I will put the solution online. So I will let you try on your own here, and I will give you the solution later. Okay, so there is two small problems using those equations and those equations, and I will let you try it on your own. Okay, so that was for the small apartheid on how to do things. I think it's very important because geomorphology is not about only learning from your teacher, it's also learning to do and have skills. Yes, Aditya?
No, it's fine. Let's continue.
Okay. So let me go back to my PowerPoint. Okay, so we are back to Unzen volcano, which is a brother or sister volcano from Gunung Merapi. And you have large blocks transported like this one here. And the volcano looks a bit different than Merapi because the lava dome is outside right there. And by collapsing, the lava dome created a lot of debris flow. And if you have been to Gunung Merapi, you are used to see this kind of facies, which are debris flow facies here. So I'm going to talk to you about debris flow because debris flow is what I love the most. It's my specialty. And also because they are very important for Indonesia. Because of climate change, heavy rainfall are going to come more often in Indonesia as well. And you might have more rainfall and more debris flow due to this rainfall. So what is a debris flow? A debris flow is a mixture of debris and water that flow rapidly on and from alpine slopes or on and from volcanic slopes. And in that case, it's called a lahar. So in your case, in Indonesia, you're going to have a lot of lahar. The concentration of debris flow can vary from debris flow to a hyperconcentrated flow. This diminution in sediment concentration usually occurs towards the end of the flow. Okay? So that's the main definition of a debris flow. It doesn't go on. Okay, sorry. So we have a lot of words in that. And what is a debris flow? What it is made of? That's what I'm going to explain. First, it is not a deposit. Do not mix up deposit, landform, and the process. Debris flow is a process. And within debris flow, we separate those that flows from the mountain, the alpine flanks, from the volcanoes. And in that case, we call them lahar. And in normal mountain, we call them debris flow. Then we make a differentiation also based on the sediment concentration. We can have hyperconcentrated flow or debris flow. And in lahar as well, we separate hyperconcentrated flow and debris flow. In Indonesian, you usually make the difference between banjir and lahar here. In English, it's a bit different. We call all of this lahar, and lahar inside, di dalam lahar, we make a difference between hyperconcentrated flow and debris flow. Okay. And earlier, I was showing you a picture with the mud flow, and I was telling you mud flow is a bit of a difficulty because it's a bit different. So mud flow are debris flow, but they are debris flow that are made with a lot of fine material. There is less large block. It's all very, very tiny rocks and tiny sediments inside. So what about the sediment concentration and how do we calculate it? So the sediment concentration is the ratio of debris of dry material per volume of water, and we concentrate it by volume or by weight. And in which case debris flow are 80% and more of the mass when you have a concentration of sediment. So the dry sediment is 80% or more, or 60% or more of the volume. And for hyperconcentrated flow, those values are 40-80, 20-60. And for mud flow, we say that we have clays between 6 and 7%. Okay? So that's the recipe for a good debris flow. You need relief, steep slopes, and all those elements to get a debris flow. Okay? So for me, that's all I wanted to talk to you about, just 1 hour in English, because English is hard. It's hard for everyone. I think I'm French, so English is hard for me too. So I don't want to give you too many elements together. What I want you to be able to do is to also reflect back on this. So this is also very important because it's going to give you tools to solve problems. One of the future of geomorphology is to use more physics, more math to solve their problems. So have a look at those equations again and try to answer those questions, okay? So thank you for having me today. It's 11:56, we have 4 more minutes. So during those 4 more minutes, I'm happy to take any questions. So if you have any questions, please ask, it's the right time now.
Ya, mari mahasiswa, jika ada pertanyaan, silahkan raise your hand or turn on your mic. I believe all of you is confused because it's about the process and mathematical equation, but it's okay. This is the first time we conduct the lecture using English, and this is the first time also we talk a lot about mathematics, Christopher. So that's good for the students.
Okay.
Mahasiswa, jika ada pertanyaan silahkan terkait dengan materi yang sudah disampaikan oleh Profesor Christopher Gomez. Ada pertanyaan? Silakan.
Kalau ada apa-apa ya, nanti pakai email saja boleh juga.
Yeah. Alright, belum ada, Chris, sejauh ini belum ada pertanyaan.
Okay.
Okay, let's start. Can I have you a question?
Yes, please.
Ini pertanyaan simple saja. You say before in the volcanic flank, if the erosion getting higher and intense happen in the volcanic flank,
yes,
the volcanic will become flat, or the hill will become flat.
Yeah.
But if the volcano is still active, it will give the new material in the flank, right?
Yes, correct. So you are absolutely right. Aditya, yes, please.
So your equation that you say before you draw the Merapi, and then the Merapi will erode, and then the slope will getting the
Yes.
slope getting low and become flat. It's only happen when the Merapi volcano stop is inactive. I mean, tidak aktif.
Yes. So what
Saya coba sampaikan dalam bahasa Indonesia, Chris. Let me try to
Yes.
sampaikan dalam bahasa Indonesia. Jadi tadi ada teori bahwa disampaikan bahwa ada erosi di lereng Merapi akan terus berjalan, kemudian akibatnya adalah lereng akan semakin landai dan pada akhirnya akan menjadi datar. Nah, bagaimana dengan Merapi yang masih aktif? Kan lereng Merapi tersebut akan terisi oleh material baru dari Merapi. Jadi, apakah contoh ini hanya sesuai untuk gunung api atau lereng yang sudah tidak aktif? Dalam hal ini adalah proses vulkaniknya. Yes, Chris, please.
Okay. Kalau Merapi masih aktif, ya, boundary condition di atas akan, you need to change it. So here, can we say it? Okay. So I was talking about the boundary conditions here. And if we keep this as 0 or no change, this means that it's not active or not eroding. But you can do two things. You can erode your volcano, or you can choose to also have here at the boundary condition more material to come in. So your boundary conditions here goes up. So if for every time step, you have a boundary condition which is going to change as a rate. So let's say for every second, you have a rate of x, or x is a wrong name, let's say m, for instance, m centimeters of material, so that it goes up by m centimeters every time. You can also use the same graph than this one. So here, this is the boundary condition here. You can use the boundary conditions at the top and decide that, okay, so we have no material for 10 years. This is 10 years. And then all of a sudden we have eruption and you have material coming in. Then nothing for 10 years, then eruption, then eruption. So this is going to modify your boundary condition. So you are totally right. The model I was explaining before did not take into account eruptions, but you can put them inside your model and see how it's balancing one another.
Okay, okay, thank you very much. Mahasiswa, ada pertanyaan lagi enggak? Monggo, silahkan. Bisa disampaikan dalam bahasa Indonesia. Nanti saya bantu translate sebisa saya.
Thank you.
Mahasiswa?
Yeah,
I think still shy, Chris. All of them is shy for talking to you.
Ya, semua malu ya. Apalagi di bahasa Inggris susah ya. Tak apa-apa, nanti aja ya. Okay, so today I think it's 12 already today. Aditya, thank you so much for having me today. I can see your young daughters at the back. Hello. Oh, your son.
That one boy.
Oh, boy, your son. Oh, sorry.
Because the hair is gondrong.
Yeah. Okay, have a good week and a good Jumatan today. And I will see you next week for another lecture with less mathematics. Hello.
This is a girl.
Okay.
Doctor, there's a medical doctor. All right.
Okay, see
Thank
you
very much.
Thanks a lot.
Yeah.